Good afternoon, everyone. Thanks, Jennifer, for the introduction. My name is Nicky Battista. I'm a research associate with CSIC. And together with my colleague, Alun Thomas, today we will be presenting a project which is looking at analyzing the structural behavior of sprayed concrete lined tunnel junctions, where we're combining monitoring data with advanced computer modeling. Those of you who have been following CSIC for a few years might remember the origins of this project. Back in 2014, I led the team that instrumented a section of the tunnel lining at Crossrail's Liverpool Street Station using a system of distributed fibre optic sensors. At the time, we had monitored the changes in strain that were occurring within the tunnel lining when cross passages were being excavated. And that data that we had acquired at the time from this monitoring are now being used to validate and potentially improve, we hope, the design methods used for SCL tunnel junctions. The main focus of this presentation today will be on the analysis and modeling that we're doing now, which will be presented by Alun, who is leading this phase of the project. But first, I will give you an introduction to the original monitoring project itself. So for those of you not familiar with Crossrail, this is a map of London. And the Crossrail route spans east to west across the City of London and Greater London. And it consists of a 136-kilometer railway line. And the project itself included the excavation of 21 kilometers of new twin-bore tunnels, and also the construction of 10 new stations, 6 of which were underground within central London. Today, we'll be talking about this project concerned with this particular station, Liverpool Street, in the middle of London. And that's an isometric view of the underground at Liverpool Street Station. And you can see this, let me try and get the pointer running. Well, you can see my mouse, I hope. You can see the station tunnels themselves. There are the 3 tunnels that run right to left, or left to right in this image. You've got the 2 platform tunnels on either side of the concourse tunnel. And you can also see here that it was a very difficult excavation sequence because the Liverpool Street Station tunnels weave through existing tunnels in London. You've got the central line of the tube system over here. You've got the Metropolitan Circle line shown in yellow, and you've got the Northern line shown in black, and you've also got this used Royal Mail tunnel going over the Liverpool Street Station tunnels. So it was quite a complex excavation sequence. The platform tunnels are 240 meters long, and the 3 tunnels themselves are connected with a number of cross passages. You can see them here, and where the cross passages link to the main tunnels are enlarged in what are called enlargement chambers. This is a view of down the access shaft in Finsbury Circus. This was the only access during the construction of the station, and anything that needed to go in and out of the tunnel came through this shaft. And access, human access to the tunnel was through this staircase here, over 200 steps. And you can see it's about 50 meters deep here, and that's how deep the tunnel is under London. This project focuses on the western side of this station, particularly on the area known as Enlargement Chamber CH5 of the Concourse Tunnel, which is linked to the westbound and eastbound platform tunnels with CP1, Cross Passage 1 and Cross Passage 2. That's a view of this enlargement chamber of the Concourse Tunnel. And you can see the size there compared with the people in this image. It's got about 11 meters diameter, and those are the 2 cross passages which will eventually link the Concourse Tunnel the eastbound and westbound platform tunnels. I say eventually, obviously now they're linked, but when this photo was taken during the instrumentation, they hadn't been yet excavated. And these cross passages are excavated in two phases. First, they are excavated to a diameter of 5.5 meters, which is called the pilot tunnel. And then that pilot tunnel is enlarged, re-excavated in a way to its final diameter of 7.2 meters. And the excavation sequence happens with a mechanical excavator doing excavations of 1 meter at a time. And after each meter, the excavated soil surface is sprayed with concrete. And I have a little video showing part of that sequence later. The image on the right is a plan view of this enlargement chamber CH5 with CP1 on the left and CP2 on the right. And in green here, I'm highlighting what's called the primary lining, which is nominal 200 millimeter thick sprayed concrete lining. And in the enlargement chambers, this is thickened to a total of 800 millimeters, so 4 times the nominal thickness, in order to take the expected additional strains that will happen when these big holes are punched into the sides of the main tunnel. The main tunnel is typically called the pairing tunnel, for those of you not familiar with the jargon. And the tunnels to the sides that are excavated later, the cross passages, those are called the child tunnels. You might hear us referring to them in that way during the presentation. So in cross section, the pairing tunnel looks like this in schematic fashion. You've got the nominal primary lining, which is 20 centimeters, and this is thickened with various layers to a total of 80 centimeters in total thickness. And this is steel fiber reinforced sprayed concrete with additional rebar in the case of the final thickening layer. So you can imagine having 6 of these, 6 pairs of cross passages. You have many junctions like this in Liverpool Street Station, and this amounts to quite a lot of sprayed concrete. And sprayed concrete, first of all, costs money. It's got a large carbon footprint, and it is also a very dangerous operation in terms of the construction sequence. And I'll show you a little clip later on to illustrate it. So anything that can help to reduce this amount of sprayed concrete would be really beneficial. And this was the primary aim of this project, to investigate, to be able to get more data on how these linings behave in order to see whether we can actually reduce this amount of sprayed concrete that goes into these tunnel junctions. This is a video that I filmed while we were in the tunnel. This is the spraying of a similar cross passage, not the one we're talking about, but a similar one a few meters away in the same station. And I'll play the video and I'll lower the volume because it's a very noisy, very loud video. And anywhere around this spraying activity, there is typically a large exclusion zone where no one is allowed to get close to the spraying activities except these 3 operatives. And these operatives are trained to remote control the nozzle gun and at the same time survey the surface of the lining as it's being sprayed to make sure that enough concrete is sprayed but not too much. And this concrete is, remember, it's fresh concrete, and it's not the first time that pieces of this concrete fall. And that's why no one is allowed to get anywhere near the sprayed surface until the concrete is hardened and then the exclusion zone is removed. So as I said before, this is a very dangerous operation, and anything that helps us to reduce the amount of concrete spraying is very welcome. So as I said before, the objective of the original monitoring project was to obtain real data, with which to validate the design assumptions through finite element modeling and computer analyses. And that is actually what we are doing now in this phase of the project. Why did we go for distributed fiber optic sensors? The reason was that all other existing monitoring systems give us point measurements within the lining of the tunnel. So if you embed pressure cells, for example, or if you fix optical displacement measurement systems to the surface of the lining, those give you point measurements of what's happening where the sensor is installed. Whereas what we really need in this case is a kind of global picture, a more distributed picture of the strains as they are changing within the lining during the excavation of these cross passages. And that's what distributed fiber optic sensors can give us, as I'll show in a minute. So those are the outlines there showing the two eventual cross passages. And that's the layout of how we installed the distributed fiber optic sensing system. It was installed in 4 parts. We've got 2 rings, one on either side of the cross passages to measure the hoop strain on either side of the cross passage excavations. And we also had 2 kind of curved rectangles, one around each of the cross passages. These cables, these fiber optic cables, were installed on the primary lining when it was 40 centimeters thick, before the additional 40 centimeter thickening was sprayed on. So essentially the cables are embedded more or less in the center of the combined 80 centimeter thick lining. So unfortunately, soon after the installation of the cables, the ring the rectangle that just disappeared off your slide was damaged by the construction activities. So we lost a part of the instrumentation, but luckily we can safely assume that the tunnel behaves more or less symmetrically, and we can focus on what's happening around CP1, and we can safely assume that it's similar to what's happening around CP2 for the same activities, for the same excavation activities. So after the thickening layer was sprayed onto the cables, and when it gained enough strength, the excavation of the cross passages started, and this starts with what's called the breaking out of the pilot tunnel. And this video shows what the breaking out means. Again, I'll start it and reduce the volume as much as I can. And you can see that it's a very noisy activity. And it's you've got this big excavator here hacking away at the lining of the parent tunnel, exposing the clay surface behind. And you've got an operative here semi-enthusiastically spraying the air to reduce the amount of dust that's generated from the excavation. And to the left, you'll be able to see in a minute our fiber optic cables coming out of the thickening concrete. You can see them here coming out of the thickening concrete, leading to the fiber optic junction box where all the individual pieces of the instrumentation were joined together and joined to an extension cable, a fiber optic extension cable, which was installed about 50 meters down the tunnel where we had our fiber optic analyzer housed in a cabin at a safe distance away. And that's where the monitoring was happening during the excavation of these cross passages. So I'll show you quickly some of the data that was obtained during the excavation sequences. So the excavation of the cross passages happened over a period, happened in 4 stages, as I mentioned before: the 2 pilot tunnels and the 2 enlargement chambers. Sorry, the 2 enlargements of the cross passages. During each of the excavation sequences, we were monitoring every half an hour. So we're acquiring data every half an hour, and those kind of half an hour snapshots of the state of strain within the parent tunnel lining. I'm not going to show you all of them, but I'm going to show you the end state of each of those excavation sequences, starting with after the CP1 pilot tunnel was completed. So here you've got a kind of mirror image of this instrumentation here. I'm showing it mirrored in the data in the form of a strain map with CP1 on the right and CP2 on the left. And this strain map shows compressive strains towards the blues and tensile strains towards the reds. And after the CP1 pilot tunnel was completed, we can see that there is very little increase in strain. We're in the maximum kind of 200 and a bit microstrain region. Then after the pilot tunnel of CP2 was excavated, we can see a little bit more increase in strain. Then when CP1 was fully excavated, again, you can see some more increase of compressive strain to the sides of the cross passage, and the start of a little bit of tensile strain above and below the cross passage. And again, CP2 completion increased the compressive strain to the sides in the hoop direction to the sides of the cross passages, and you can see tensile strain in the longitudinal direction, mostly below the cross passage, but also somewhat above the cross passage as well. And this is this pattern of strain is what would be expected, because the strains are redistributed in an arching fashion. So as we punch this big hole in the parent tunnel, the strains from the loads above and to the sides are redistributed around this hole, forming this arching effect, which is trying to open up beneath the cross passage. But to me, what was very interesting was that if we zoom in around the cross passage and look at the hoop strains, we see that most of the change happens very close to this big opening that we just made. So about half a meter away, we had our first hoop strain measurement, and that's where we see the increase in strains up to about 800 microstrain. Remember that we are talking about change in strain here from the initial constructed state to the excavated state. But even if we move just 2 meters away, there's hardly any increase in the strain in the hoop direction. And this leads one to think whether perhaps we can reduce the extent of this thickening. So for example, here, if we limit the extent of the thickening of the lining to, say, 3 meters on either side of the cross passage, then we remain with this part shown in red, which we could say is not doing much. And this is one of the aspects that we've been looking at through the computer analyses that we're doing in this next phase. And now I'll stop sharing my screen and I'll hand over to Alun for him to talk about what we're doing now with these data.
Great, thank you very much, Nicky. It's a great pleasure to be able to present this and to do this work. For those of you who know me, or for those of you who don't know me, I was involved in the original design, and so it's quite special to be able to come back and look at what was measured during construction and how that relates to what we had. So that was the basic goal of this current phase, was to essentially rerun models and see how do they compare and what can we learn from that. And that process of, in a sense, calibrating the design approach was critical for us to be able to build Crossrail. So what you see on the right-hand side are some pictures from the original calibration that we did, where we used data from the Heathrow Express and London Bridge from the Jubilee Line extension, and got that to use that to calibrate particularly 2D models that we used as the workhorse for the design originally. So learning from these successful projects is incredibly important. I'm going to move pretty quickly through this, but before I sort of go into the detail of what we've seen from the modelling, I'd like to remind us of the context. So this is a form of construction where everything that is sprayed is part of the permanent works. Now that differed from what was done previously in places like the Heathrow Express, for example, where there was a cast in situ lining. So there are some quite novel aspects to this, and there are areas that are still not fully understood. In terms of the actual design of the junctions, because there were so many, and we had 5 or 6 stations to design, the approach we took was to do a parametric study with the 3D model. It was done by my colleagues in the Budapest office of Mott MacDonald. From that parametric study, we created some design charts, And we combine that with the standard 2D cross sections that were done at regular intervals along the tunnels for the stations. So that enabled us to take the information from the 2D models, elevate the loads to account for the fact that there's a junction, and then work from the design. So in general, we were not running 3D models for every single junction that we had, even though it's clearly a very three-dimensional case. So there's a sort of question about how good is that as an approach, as an approximation. What we do know is it was very successful during construction. As I think Nicky's already pointed out, it's a very constrained site. So this is a view of the Finsbury Circus site. You can see it's a heavily built up area, some quite old buildings, it's quite valuable real estates, and a lot of people working there. So lots of things for us to take care of, and even the process of reassuring those stakeholders. So never mind sort of the issues of safety and damage to buildings, but getting acceptance from stakeholders when you're tunneling underneath live railways, for example, is an important part of the process. And without these models, we simply couldn't do that. So just to refresh your memory, this is the area we're looking at in plan view. You've got the Northern Line in green there, the Moorgate Crossrail station box, the platform tunnels, and then this is the junction we're looking at. So it's CH5, the concourse, with connections to the platform tunnels. There's a picture borrowed from Mohammed Aristei's presentation, just to remind you of the scale. And here you can see the reinforcement being installed. As Nicky said, if we can start to minimize the amount of reinforcement we put in, then that's obviously going to make things simpler, quicker, cheaper, and be less carbon involved in the structure that we rebuilt. So, to the modelling. I've used FLAC 3D, which we used during the design. You can see the mesh here, which is obviously certain simplifications, but we can see the strata with the London clay is the main unit where you find the tunnels. At this particular station, you have obviously the Lambeth group beneath the London clay, and that includes, for example, this red layer, which is a sand layer. So that's the geology that we're looking at. One reason for using FLAC is because it's code-based, you can customize it. You can bring in some of the complicating factors, such as the variable K0 in these over-consolidated layers, and also the variable pore pressure, because you get an under-drainage effect of acting on the London clay. Also, as Nicky showed, there's quite a detailed excavation sequence, and we know that influences the prediction of loads and aligning. Therefore, that's something else to add in. Just to orientate yourself, this is CH5. You can see I've omitted a number of the other complicating sort of factors, such as the other tunnels. But we do have platform tunnel westbound in the model. And this was so we could compare the case between excavating a cross passage between two tunnels versus a cross passage going into virgin ground, and see whether that was influential. And that's the approximate dimensions. So the base case model that we have has a nonlinear elastoplastic ground model. We're looking at the undrained, the initial short-term stage, because that's what we have the results for. The diagram on the right shows the sort of variation in stiffness versus strain that you get from a Jardine type nonlinear elastic model. The modeling of the tunnel lining is simpler. Linear elastic shell elements. There is aging, so the stiffness of the model corresponds to the stiffness of the concrete at that particular point in the construction sequence. The sequence itself is quite detailed, and that I would characterize as sort of a best shot in terms of normal design process. You can, of course, make it more sophisticated, and I'll show you what we've done. But if in the commercial world, this would be seen as pretty damn good, a best shot. I'll just show you how the sequence of excavation looks. You've got CH5 in the middle here, and we have a top heading followed by a bench and invert sequence for this pilot tunnel. The coloured blocks, you can see that's the plasticity in the clay as the excavation proceeds. And you can also see the lining elements that have been put in with an exaggerated distortion, so you can see how it forms. So we've got a pilot followed by enlargement, and then it sort of completes the overall tunnel. So how does a junction actually behave? Just looking at one part of this, you can see that the crown that comes down, the invert comes up a little bit, so you get this sort of bending, this closure. If you look at the hoop forces in the lining, you can see away from the lining it's fairly constant, but you get a concentration, which some people have likened to a flow of stress around this hole. You can see the concentration with higher and compression in the blue areas, and potentially tensile splitting in the red areas as those lines of stress diverge. You also, in the longitudinal direction, you see the same effects, but you have to remember the longitudinal forces are believed to be much lower, let's say 10 or 20% of the hoop forces. However, besides that phenomenon, you can also see substantial bending in the crown. So as the aspect ratio of the child and parent junction increases, in other words, as the child tunnel gets bigger compared to the parent's tunnel, this area in the crown becomes a little bit like a flat plate. And consequently, you can see it bending, particularly under this vertical gravitational load here. It bends more than underneath. So there are some competing mechanisms at play here, which I'll try and show in the results later. And those are the concentrations that you would expect in terms of forces. So how do these models perform in terms of a broad sort of characterization? I'd say that they're working pretty well. We're seeing it behave the way we'd expect to see. Previously, I showed you the area of sort of plasticity around the tunnel. It's quite local, which you'd expect for these smaller tunnels coming from larger ones. Same for the sort of the changes in pore pressure around the tunnel. If you take volume loss, which is a crude metric, but it's a gauge. I've plotted here the volume losses associated with some of the different models, and you can see they compare quite well with the sort of range of volume losses that are reported for other tunnels, similar tunnels on Crossrail, so for 0.4 to 0.55% volume loss. I can explain a little bit more about that. So that led to us feeling reasonably confident we've got a reasonable model that was running and doing something realistic. Now I'm going to try and dive into the nitty-gritty and look at the actual results in comparison with the measurements that Nicky and his team made. So just to remind you, this is the arrangement of fibre optics up here. And I'm going to look at this loop, which is just beside the opening, so ½ meter away from the edge of the opening. And this graph plots the actual measurements, this blue line, if you can see my cursor. And at the 0 marks the crown, and then we've sort of unwrapped this loop, and you can see the cross passage 2 on the left in that region, and cross passage 1 on the right. So at this point, this is when the pilot tunnels have been broken out. You can see that the pattern and the magnitudes predicted by the base case model is reasonable, perhaps a bit on the low side, but the pattern seems to match the results. If we roll forward in time to the situation when both cross passages have been fully completed, you can see that the base case is under predicting. So in other words, it seems to be stiffer than the actual measurements. So there's a certain discrepancy there. If we look at this sort of chord 2 meters away, so it's in the sort of the sidewall of the lining, and again we start off at the beginning of the excavation process, the pilot tunnel. Very, very small movements, or strains rather, as Nicky said. So it's you see quite local effects. And similarly, the models show very little change in in strain. These are all changes in strain as opposed to absolute numbers. And then we roll forward to when all the openings are fully developed. In this case, the relatively stiff base case model matches the results pretty well. If we turn to the other sections, so the sections above and below the opening, so this line here I'm showing you, this is data from above the opening. The grey line with the dots, those are the measurements taken, and that's from the stage when the cross passages are fully developed. So both enlargements have been completed. And you can see below the base case results. And that reflects, although admittedly this is a work in progress, I believe that reflects a lot of the bending. So you can see there's a tensile change in the strain, which would be consistent with a sagging bending behaviour in the crown here. And the model shows the same pattern, albeit with slightly different magnitude. That whole area is an interesting one and a complex one. There seems to be a little bit of a correlation with some of the pattern and the location of the reinforcement that was placed. Not exactly sure why that is, but there appears to be some sort of correlation there. And also we have to remember that it's an area where there are quite a few different parts to the construction process. So for example, there was a window, so the lining is slightly thinner in certain locations, and that intersects with the morphing point. So that's an area we'll continue to look at to try and understand how to model it better, or why there are differences between those points. So we've been looking at strains so far, which is great, but as a designer, we check loads. So from the model, of course, we can extract hoop forces or longitudinal forces and the corresponding bending moments. So now I'm going to look at a line. If you imagine a line along the axis of the tunnel from the edge of the opening, I've plotted below on the left the axial force normalized with the axial force before the openings. So this is showing you how much the axial force is elevated. So these blue sort of concentrations, how high are they in comparison with the normal green versus the distance away from the opening. And you can see the red line is the base case beside cross passage 1, and within a very local area, so less than sort of 3 meters, you see that the axial forces escalates very rapidly. Interestingly, it is less pronounced for the, it's more pronounced for CP2 than CP1. And also, when you look at the platform tunnel westbound, if you remember, one of the cross passages goes from CH5 and connects to the other cross passage, the other platform tunnel. There's a much smaller impact on the receiving parent than the parent from which the child breaks out, which is an interesting sort of side note. I've tried to drag out some data from Heathrow Express from pressure cells, and that seems to correlate reasonably well with the sorts of increases in axial forces we're seeing. Bending moments are very interesting to look at because they tend to govern the design, and you can see again a rapid increase in bending moments close to the opening, and it's more pronounced for the receiving parent. It's more pronounced for the parent from which the child breaks out than the receiving parent, the brown line being platform tunnel westbound. Nicky was raising the question about, can we change this thickening? We had a rule in the design team of half the diameter of the child tunnel. That was the extent of the thickening. That was based on increasing the hoop load to 120% of the original value. So this diagram would suggest that there could be scope to play with that, to reduce it a bit. If we take a look at the other measurement that we generally have, which is the lining deformations, you have convergence points put into the lining. I've plotted here some data from Mohammed Ariste's presentation, which is from Farringdon, but so similar tunnels, but in a different station. The reason being that I haven't been able to pin down the exact data for Liverpool Street yet. But it seems to match reasonably well with the red line, which is showing you the base case model. So the deformations of the lining from those separate independent measurements seem to be consistent with the strains in the model that we're seeing from Liverpool Street. I'm going to very briefly give you a snippet of the things that we've looked at. Broadly speaking, we've looked at the constitutive modelling of the lining itself, specifically nonlinear elastic behaviour of the lining. We've also looked at sequence, and then we're still looking at this the behaviour inside the cross passage itself, where you see in the model you see a lot of longitudinal tension, but we're not actually convinced that that appears in reality. So I'll give you a brief teaser of some of the results. Firstly, the nonlinear elastic model. So again, I'm going back to looking at these loops. If I can go back a step, this is 2 meters away, and it's pretty similar to the base case and the readings. That sounds good. If we look at the results at 0.5 meter, being inherently a softer model, the nonlinear model, it changes, it softens as you stress the concrete. We get more strain, and that seems to fit the measured data better. So this is looking at this loop in the hoop direction. If we compare the loads, the axial forces tend to be lower in the nonlinear elastic model, which would be good potentially for our lining design, and the bending moments are pretty similar, slightly higher in certain places, but it changes depending where you are in the cross section. Turning to sequence, 2 aspects we looked at. One was, does it matter if we build the CP1 first or CP2 first? Do we have to do the pilot on both sides and then the enlargement, or do the pilot and the enlargement on one side and go over to the other side? That doesn't seem to matter. So that gives us some insight into the flexibility, the room for maneuver in choosing a sequence. The brown line on this graph here is what I call the Greenfield case. So there we don't have platform tunnel westbound in the model. So we just have CH5 on its own with the cross passages. And if you compare the brown line to the red line, which is the base case, you can see that omitting the neighboring tunnels leads to a prediction of less strain in the lining, and you'll also see lower loads. So in other words, if you do have tunnels close by, it is important to put them in, because they will elevate the loads on your tunnel. So and then this is looking at the situation when both pilots have been fully developed, and you can see the change in sequence made no difference. The green and the red lines virtually match, but if you omit the platform tunnel, then you would expect to see less strains. These are the corresponding data points from the axial force at the top right, with distance from the opening. You can see slightly lower values for the Greenfield case. The difference in sequence makes a negligible difference. So to round off, looking at the lining capacity. So what we do as engineers very often is we're comparing the loads from our calculations with the capacity. Here we have an axial force moment interaction diagram. I've put on the dots from the base case model, and we can compare them with the capacity of the lining. So the dashed line represents the thickness, is 800 millimeter thickness, without any extra steel bars in it. And then the grey line shows the additional reinforcement. It's slightly complicated because you get different reinforcement in different parts around the hoop, around the ring. But this is an indication of the maximum reinforcement in the the junction that was built. So you can see that that broadly matches. My base case is slightly different from the actual original design, which you can see in red here, which obviously does fit within the capacity of the lining as designed. If we look at the nonlinear model, so changing from a linear elastic model for the sprayed concrete lining to a nonlinear elastic, there's a substantial change to the loads. And that would suggest that we could have thinner, less heavily reinforced linings. So these are results based on the 800 thick lining. I've then rerun this model based on sort of a guess that perhaps 600 millimeters would suffice. By changing the thickness in a design calculation, you change the answer that comes out the end, so you have to be a little bit careful of how that loop runs. But if I compare these light green dots, so those are the predictions with a nonlinear elastic model 600 millimeters thick, with the capacity of a lining without any reinforcement at 600 millimeters thick, it almost works. So with a bit of clever design, that suggests to me that we could be going from 800 to 600 and reducing quite a lot of the reinforcement. What does that mean for our carbon footprint? Well, you can see in the top right, if you look at the materials, the cement in the concrete has a huge impact. So basically we're looking at cement and to a lesser extent, much lesser extent, steel as being the primary culprits for the contribution to the carbon footprint. What could we do? Well, we could omit quite a few of those bars if we were able to use a nonlinear elastic model. We could also use lower carbon materials such as macrosynthetic fibres instead of steel fibres. So that would have a significant impact on the carbon footprint. We could probably go from 800 millimeters down to 600. And as we've already sort of looked at, that extent of thickening could potentially be reduced, that the area beyond 0.5 times the child diameter could have been omitted. And when you wrap all of that together, you're looking at a substantial saving in the carbon footprint. You're cutting off at least a third, maybe much more, maybe closer to half of the total embodied carbon in that junction. You replicate that over 30 junctions per station, and all these, and it adds up. It may not, it's still, I would agree that it's still a small component of the overall project, but we need to be able to make savings in any areas we can, and this is one definitely to look at in the future. So to wrap up, after this whirlwind tour, the original work by Nicky proved that we can put in fibre optic loops in that very demanding environment of a sprayed concrete lining. We can spray them in. They give us very detailed information, a distributed picture as opposed to spot data. There's some lessons learned from how to put them in and how to get the best out of the data. Looking at the modelling, we can see that there's still a gap between what we believe is happening, what we've seen measured, if we assume those measurements are completely accurate, and what we are predicting. So there's an area to look at. Non-linearity in the concrete could well be the answer to some of that. There's some scope to play with excavation sequence. Maybe we don't even need the pilots at all. And that would make it easier to build these tunnels. And we could also probably use better design methods to reduce the carbon footprint as well as the financial cost of what we're building. This is a work in progress, so we're still looking at some elements of that, and we're hoping to keep ongoing with this process of sort of learning from the successes and feeding that back into the industry. So thank you very much